Okay, so a pin is squeezed between a finger and thumb. Which statement is correct? The force on the pin is larger on the finger than on the thumb. No, that's not true. The forces are going to be equal and opposite. So let's off that one. Force on the pin is larger than on the thumb than on the finger. Nope. Again, their forces are equal. That's not what's different here. The pressure of the pin is larger on the finger than on the thumb. No, you can see here the area is much bigger on the finger, which is going to make the pressure smaller. So the pressure of the pin is larger on the thumb than the finger. Yeah, that makes sense. There is a really small area in contact with the thumb, so a really big pressure. That's why it hurts and does damage. So two boys, X and Y, each have the same total weight and are standing on snow. Which boy is more likely to sink into the snow and why? So if we look, X has a really small area in contact with the ground. Y has a really big area. So Y is going to have a lower pressure, X is going to have a higher pressure. So it's going to be X that's most likely. So first of all, we can get rid of C and D. They have the wrong answer. And X, because the pressure is larger than Y. So it's going to be option A. So an elephant has a weight of 44,000 newtons, and each foot covers an area of 0.025 meters squared. A woman's stiletto heels has a weight of 660 newtons, and the total area of her shoes in contact with the ground is 0.0015. Who exerts the greater pressure? So the equation we need is pressure is force divided by area. So the pressure of the elephant is going to be 44,000, and it says each foot has an area of 0.025. So that's going to give us a total pressure of 4.4 times 10 to the 5 pascals, whereas the pressure of the woman is going to be 60. It's total area, so we don't need to do any multiplying by 2, and that is, wouldn't you know it, it is 4.4 times 10 to the 5 pascals. So essentially, it asks which exerts, so we haven't actually answered the question yet. So they both exert the same pressure. So now we've actually... So when a pressure of 4 newtons per millimeter squared or more is applied to your skin, it hurts. A man of weight 660 newtons, but everyone seems to be 660 newtons these days, lies on a bed of nails, each having an area of 0.5 millimeters squared. How many nails must he lie on if it's not going to hurt? So, pressure is force divided by area. So the area you would have to lie on, we'd need to do the force divided by the pressure for it not to hurt. So we're going to do 660 divided by 4. 600 divided by 4, 150. 60 divided by 4 is like 12.5. So 660 divided by 4 gives us 165 millimeters squared. How do we know it's millimeters squared? Well, we had the pressure in newtons per millimeter squared, so it's going to output the area in millimeters squared. So if each, so essentially 0.5 times by the number of nails has to be 165. So n is 165 divided by 0.5, so essentially double that, and that's going to be 330 nails. Okay, so the pressure due to Earth's atmosphere varies from place to place and with atmospheric conditions. The standard atmospheric pressure is defined to be 101,325 pascals. Estimate the area of a typical window and hence calculate the size of the force due to air pressure. So if we sketch a window, I reckon a solid size is 1 meter by 1 meter. If you see in here, it says estimate. So I'm going to round to like the nearest easy number. So So the area is going to be 1 meter squared. So pressure is force divided by area. So the force is pressure times by area. So it's going to be essentially 101,325 times by 1. So it's about 10 to the power of 5 newtons. So I've rounded to one significant figure because we're just estimating, and our lengths were both one significant figure anyway. So this is roughly what the force on a window is, and you'll notice that is a very big number. So why does this force not have any effect on a normal window? So both sides are subject to 10 to the 5 newtons, therefore resultant force is 0. So that's why we don't notice, because we've got both sides subject to atmospheric pressure. If we have one side of a window that is a vacuum, you can see we get a massive force acting on it, which is why it's so difficult to send things into space, where one side of things is at basically 0 pressure and the other one's quite close to atmospheric pressure. That creates massive forces on things. Okay, so water has a density of 1 gram per centimeter cubed. We want the pressure exerted by 500 milliliters of water on the bottom of a beaker, and we've got its diameter. So first of all, to get its area, we need to do pi r squared, which is going to be pi times by 0.15 divided by 2 all squared, which is equal to 0.016 blah 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 meters squared. The force is going to be the weight, which is mass times gravity, which is equal to that. It's the mass times gravitational field strength, just using the density equation. So because we've got the density in grams per centimeter cubed and the volume in milliliters, we don't actually need to make any conversion here, because a milliliter and a centimeter cubed are the same size. So you can see that that comes out as 5,000. That's going to be needed to divide by 1,000. Why? Because that's going to output the mass in grams. So we need to divide by 5,000, which gives you 5 newtons. And then pressure is force divided by area. So we're going to do 5 divided by 0.017, which is equal to 282.9 blah blah blah, which is just 2.8 times 10 to the 2 pascals to 2 significant figures. Or I guess we could write that as 280 pascals if we're being a bit more vague.